Happy PyTorchCon. Hope everyone has learned a lot. I sure have. I was at yesterday's poster sessions at the compiler section. It was just amazing what people are doing there. So my name is Niels Bantilan. I'm the Chief ML Engineer at Union.ai, where I'm helping to build, maintain, and commercialize Flight, which is an open source ML AI orchestrator. But today, I'm kind of putting on a quasi kind of research engineering hat, and super excited to talk to you about sharing my learnings from designing and building custom RL environments for fine-tuning language models to perform multi-step reasoning tasks. So it's crazy to think that DeepSeek R1, the paper and the model, came out just in January and caused a lot of hubbub, a lot of price fluctuations, as we all know. But the one thing that it inspired me to do, I think, is kind of captured in this post by Andrej Karpathy, which is basically saying one of the highest leverage things we can do as an open source ML, RL, AI research community is to build high diversity RL environments. And as he mentions here, this is a highly parallelizable task. So I guess I'm one of the units, or one of the execution paths in that massive fan out that I think we're currently engaging in as a community. So we have all these great training tools and infrastructure, and I think we still face a major bottleneck to getting the most out of these RLHF, RLVR systems. And I think one of these bottlenecks is, as was pointed out earlier in the previous slide, the creation of diverse RL training environments that elicit kind of like these multi-step reasoning traces that will allow language models to do useful things in production at inference time. And so one of the main points in my talk is that we're not really, if you look out there at a lot of the training frameworks and the training code out there around RLVR, we're not really fully utilizing like the full RL API, this agent observation loop where the agent takes actions which affect the environment, which then affects the next set of data points it sees, right? So what we see, I think, for the most part, not all projects are like this, but for the most part, we have these static data sets, these math data sets, these coding data sets with problem and solution pairs. And if you squint and you look at it, it's essentially like IID data set sampling from this data set. The actions that the agent takes are kind of no-ops in the environment. They don't actually change what the agent sees next, right? You have these rollouts that you have the agent solve an equation, then it has the solution, and then what happens next? Really nothing, you just get the next data point. So the crux of my talk is, it's kind of a call to action, which is by moving towards fully fledged RL training environments, we can expand the class of problems that RLVR can solve beyond math and coding problems to these basically single-step reasoning tasks to multi-step reasoning tasks. So you can fine-tune language models in a setting that more aligns, at least, with real-world kind of agentic problems. So I want to spend a few minutes just to get everyone on the same page. I'm not sure how many of y'all have looked at GRPO recently, but really the crux of it is when you compare it to proximal policy optimization, which is at the top, you have basically three models: the policy, the reference, and the value model, right? So GRPO gets rid of value model, which substantially simplifies the training loop, and instead uses a batch of rollouts to get a bunch of rewards, which you then use to compute the advantages. Advantages basically being how much better do you do for a given action based on some like mean action. So if you look at the data sets out there, like the Numina math data set, you have problem solution pairs, and you have a function, in this case, this accuracy reward function, that's responsible for parsing the completions that the agent produces, parsing the solution, and then administering some kind of reward based on a match of a solution to answer. So what are we missing in this setting, right? As I alluded to earlier, we have a static data set with an oracle, some kind of algorithmically derived or a human label, some sort of way for us to write a function that says, here is the correct answer, right? And you get a +1 or a 0 or a -1 based on the answer, the correctness of the answer you provide. Actions, as I said earlier, are no-ops. The actions at the end of this rollout trajectory don't actually affect what the agent sees next. And the states that the agent sees can't really model temporal dependencies across actions and states because you're just getting these math problem sets or coding problem sets just sampled out of this static data set. So this work centers around the question, what might quote-unquote self-supervised RL environments beyond math encoding look like? And so for this, we take inspiration from two things. The first one is next token prediction. Let's consider for a moment the unreasonable effectiveness of next token prediction at producing these really rich language representations, right? And then you have to do RLHF to make it not act crappy or whatever, right? Or spew out the internet speech. But if we look at it, right, if you just look at the tale of two cities, the first couple of words, just this text snippet, you can derive a whole bunch of training data samples just from that, right? So this allows you to massively scale and trivially extract labels from massive amounts of data. So what might self-supervised pre-training look like for language model agents that do multiple steps of reasoning, multiple sets of actions, that gets more context into its context window, that does more work to solve a problem? So the second source of inspiration is from the classical RL grid world, right? The states here are the local representation of the agent's position on the grid. It only sees what is in the block above, below, to the left, and to the right of it, and then needs to make a decision on where it needs to go, up, down, left, right, in order to get a goal into the goal state. And you might write a reward function, something like a -1 for each time step that it's not in the goal function to incentivize it to get to that goal function sooner. And so for these two pieces of inspiration, I'm going to draw on a third data point, which is the Wikipedia citation graph. This is a massive graph. Humans have been writing and annotating and providing structure to this graph. And more broadly, the internet, right? But if we look at high-quality sources, we can stick with Wikipedia. And I hope you can kind of squint and see where I'm going with this. Who here has played the Wikipedia game? So you start off in two random nodes that are kind of n hops away. And in this game, you can only click on the links on the page, right? So you have to kind of scroll. You have to reason your way. How does Titanic relate to Zoolander, right? How many? I guess there's 1, 2, 3 hops away to get to there. So for a pre-trained language model, it's already been trained on Wikipedia. This, may be a trivial task, maybe not. I'm not sure. But if you've ever tried this, there are several websites, and it's actually kind of hard to do. So Wikipedia as a RL environment it's fairly easy to see how you can pull out like a self-supervised reward signal from this, right? So nodes are states. Agents traverse edges through actions. So they select URLs from the context window. And rewards are shaped by the target node. And here, there's a lot of reward engineering that's more art than science. And I'll share a little bit on that a little later. Work has already been done on this. There's this paper here, Learning to Navigate Wikipedia by Taking Random Walks. This, however, uses transformers to create embeddings of nodes and links, and then uses like this custom MLP to like produce probability distributions over the links. So I kind of wanted to go for something more like generalizable and purely based on token inputs and outputs, right? So tokens are the state space, and tokens are the action space. And so if we go back to this agent environment loop diagram, the state is the current state plus the target URL. So you start in the Titanic page, and you tell it, go to Zoolander. The agent is a language model. And the action is a reasoning trace and answer to what link in its current context it should go to get to the target page. And then the action is sent over to the environment. The environment sends the next state and then a reward associated with something, maybe how close it is or some set of heuristics. So this is a very simple kind of test bed for LM agent fine-tuning. And it's good to start simple to see if this even has any value or even works. So the prompt template for this, which I'll mention later, took some time to converge on, is a minimal instruction set to give the agent enough context to tell it what should go into think and answer tags. And note here that the target URL is actually in the context directly. So you have to kind of shape the reward such so that you punish it selecting the target URL if the target URL is actually not in the page content, right? So the reward function might look something like this. So you give it a -1 if it selects the target URL, but the target URL is not actually in the context. If it spews out just random stuff, you give it a -5. If it selects the next URL, which is kind of like the checkpoint on the way to the target URL that the environment used to traverse from start to end, you give it 0.5, and then 0.1 if it reaches the goal, right? So the training architecture for this looks very similar to the GRPO sort of like high-level architecture that I showed earlier. This just gives a little bit more color of what's going on, right? So the environment produces per episode, it produces some travel path. So it plucks out a random node from the graph. You say, hey, do a random walk 5 hops away or 10 hops away or 20 hops away, and that is kind of a natural way to increase the difficulty or reduce the difficulty of the problem. The agent starts on the starting node, and then it generates a bunch of completions. It goes through this whole update loop. The policy is then updated, syncs back into the rollout phase, and then selects the next action as well. And then this kind of loop keeps going until it can kind of reason its way into the target node. So from an implementation practical perspective, because I work at Union and we maintain Flight and I get free GPUs from that, I use Flight as the underlying platform to kind of orchestrate all of this. Think of Flight as kind of Ray with a few differences where the devil's in the details. Actually, a lot of people use Flight and Ray concurrently. And I'm actively developing a library called AI Gym where I'm just testing out these ideas, right? So it's an early project. I'm just testing out this Wikipedia as a graph maze idea, but hopefully, and I'll mention the goals later, that these can generalize across arbitrary graph structures. Obviously, PyTorch, this is PyTorchConf. Also using transformers and PEFT just as a convenient way to load and save and do LoRa adapters and stuff. And vLLM, which I haven't quite used yet. I'm still kind of prototyping. And obviously, I'm using the Union version of Flight to make this all work. Just to give you a sense, I don't know if the text might be a little too small there, but AI Gym is a library today. I think you can pip install it, although I don't think I've done the latest release yet. I'll get to that right after this talk. But basically, you write a policy that's kind of like your rollout function. It takes in a prompt and it produces in streaming mode, it kind of yields text chunks, right? But it also works in batch mode. And you instantiate this Wikipedia GymEnv class with nhops as a parameter. And in this case, I think if you squint, it's going from this movie called The Primevals to the page for miniseries, and it gets there in 5 hops. So this is purely the rollout phase. There's no policy updates here. It's just you're taking the base model. I think here I'm using Olama and Gemma 3 4 billion to just generate these rollouts to even test whether just like a frozen model can even solve this kind of task, and it can. In terms of the training stack components, AI Gym is responsible for basically setting the travel path per episode and then determining the rewards and determining sort of the links between the nodes. And in terms of the policy and the reference models, basically note that on the left-hand side there, on the policy model, this is inference only, right? So no gradients need to be tracked. The reference model is always frozen, so again, this completely inference mode. Reward model can be a language model also, but it's typically just a function that's evaluated. And the policy model in the middle there is where the gradients are actually required, so you need to keep track of the gradients there. And so this informs of like the simplest setup for agent environment training loop here. This is just some code in flight of how to declaratively say what resources you need some GPUs, here are the pip packages you want to install, and here I'm using PyTorch and, as I said, transformers and PEFT just for convenience. For memory saving, you can use LoRa. So this actually allows you, with a fixed GPU budget, to fit larger models, and the number of trainable parameters are orders of magnitude less. And so this is just a way for you to get higher capacity models if you need them. This is actually the current setup that I'm using for my experiments as I flesh out this project. Just want to show you an example of a multi-node setup. I'm not quite here yet, but basically this is where you can leverage tools, inference frameworks like vLLM and SGLang, right? So for that rollout policy phase and the reference model, they're inference. They're only used for inference, so you can use these frameworks for that. And then you would then use PyTorch and AutoGrad framework for the actual policy updates. Some initial experiments. This is somewhat cherry-picked, but I'm kind of starting to get consistent results here. I'm running some small-scale experiments where this is like the example configuration. I'm using Gemma 3 12 billion. I'm starting, for every episode, I anchor it to the mammal page, and then I have it do random walks around the mammal page just for consistency. Just 2 hops away, so a fairly simple problem. And some other configuration there, as you can see. So n tries per hop sets the kind of number of try budget for each episode. Some implementation challenges, I think, maybe worth noting if you ever, because I implemented this somewhat from scratch, so I didn't use TRL or VRL just because I'm a glutton for punishment and just want to, it's just hard to get these things to work. And there's a certain pride you get when you implement things from scratch-ish, just using PyTorch. So some of them actually are around the data, surprise, surprise. So the environment, designing the prompt, designing the action space required a lot of trial and error, and this is really just vibe-based. It's you write a prompt, you see how it does, you modify it, and then you pick the one that you just kind of have to stop somewhere. In terms of the state representation and validation, this was also a tough part because do you send it Markdown as context or HTML as context? I chose Markdown just because it's more human readable, but who knows, maybe HTML is better for this. And you have to do a bunch of pre-processing of the page content, doing a lot of validation to make sure the links are being correctly plucked out and linked together in the graph. Local dev on low capacity small language models is also hard because if you don't have a good prompt, it's just never going to get a valid action. And so you're trying to test that part of your execution path, and it just never gets there because it's never generating a valid action. So this is where frameworks like Ollama just really help for you to just fit a quantized high capacity model on your, I guess I have an M3. So that's very useful. One that blew up on me was managing context length. So there's a wide variability in the length of Wikipedia articles. And so this increases your input context by a lot potentially. So this could lead to out-of-memory errors. So there are a lot of design decisions you have to do to just like hack around this and limit the context length and things like this. And finally, reward engineering, which is a very much an art. You just, again, you finger to the wind. You say, when do you give the cookie and when do you like slap its hands and say like, no, bad agent. So there's a lot of trial and error there as well. Just on the debugging point, and just shameless plug of Flight and Union, I found it super useful to have a hackable debugging and observability layer to help build this project, right? So as you can see here, this is my agent training loop. It's kind of spitting out reports per step. And so I can build these rich HTML reports of what actions it's taking, what context is in its field of view at any given step. And this was invaluable for me to see various like bugs on my end and weird behavior that the LLM was outputting. So a quick note on sort of what I see as the kind of research roadmap for this kind of work. One part is parallelizing multi-step rollouts. So when you have a multi-step reasoning problem where, in this case, you can consider the tool as, the tool of creating a JSON blob with the action, the URL, in it, right? So it's just one tool that the agent has access to, but it's selecting multiple URLs over time. So we don't really have. I did a bunch of research on the literature. There's not a great way of doing this right now, and so that's one challenge. Another one I'm super interested in is off-policy GRPO. So what if you can have a high-capacity model that kind of distills its knowledge into a smaller language model? So that's kind of the gist of this. Then finally, what are the different RL task types that you can create from graphs, right? So we did graph traversal, but there's also node reconstruction and node correction and edge reconstruction, category reconstruction, and node evolution. So Wikipedia pages change over time based on discussion around it, right? So there are all these problems that I think are ripe for kind of investigation. But again, the devil's in the details of how do you actually cast this into an RL environment. Some ideas on how to generalize this to real-world problems. I'll kind of gloss over this, but really what we're interested in is like the browser use agents and the deep research environments and the business analyst agents. So this is one other challenge of how do you cast these problems into graphs so then you can train them with RL. And really the goal of AI Gym is to bridge this gap between graphs. So if you can cast your agentic application into a graph, in the future, hopefully, AI Gym would be able to take that graph and like pull out these suite of RL tasks that you can then train on. And hopefully integrate with frameworks like TRL and vRL so you don't have to implement the agent training loop from scratch. These are some related projects around this idea of fully fledged RL environments. Just want to give a quick shout out to them. These slides are also uploaded, so but yeah, feel free to take pictures. And main takeaways for this is, we should be building RL environments and not these static data sets with oracles. And yeah, I want to end. Thank you so much for attending and your attention, and hope you got something out of this. You can contact me on LinkedIn, and these are QR codes for the projects I'm involved with. Happy to talk about this or really anything else. Thank you. Oh, yeah, I guess we're done. Yeah, I'll be around, so we can chat.